Good morning, everyone. Welcome back to the third day of the workshop on online algorithms, online rounding, and the interplay between them. Today, we're happy to have Sahil Singla telling us about online contention resolution schemes. Sahil is an assistant professor at Georgia Tech, works broadly on algorithms under uncertainty. Some relevant sub-areas of this are online algorithms, AGT, stochastic optimization, and for all of these, online contention resolution schemes plays an important role, so Sahil will give us a good introduction to this today. So Sahil, take it away.
Thanks. Yeah, I hope you can hear me fine. So today I'll be talking about online contention resolution schemes. And first of all, I'd like to thank the organizers, Z and David Wykes, for inviting me. And as the name of the workshop says, it's about online algorithms, in particular about online rounding algorithms. But the setting in which you round is somewhat different from what you've seen in the past, and I'll explain this more as we go. So the way I'll be introducing, rather than directly introducing the setup, the formal setup, I'll start off with a particular problem, something called as the online Bayesian selection or the profit inequality problem. And from that, I'll introduce the definition. Just because if you directly see the definition, it might sound a little bit too abstract. Good. So here's the simple problem, which is known as profit inequality. So the problem has histories in optimal shopping theory. It was introduced in the 1970s, known as the profit inequality. But more broadly, you can call the area online Bayesian selection. The important thing is the following. So the setup is as follows. You have n independent random variables. Think of these are say, n boxes. Each box has some hidden reward inside it. Okay, so you don't know the exact value of a reward in a box, but you know the distribution from which the reward is drawn. So in this example, you have, say, 4 distributions. The first distribution is uniform between 0 and 10. The second one is maybe exponentially distributed with some parameter. D3 is like a deterministic. It's a point mass with value 2. D4 is some kind of a weighted Bernoulli distribution. So you have different distributions. The distributions are all known to you. They are crucially all independent. So towards the end, I'll mention about beyond independence, but pretty much we'll always assume independent distributions. You don't know the realizations. You get to see the realizations one by one. So there are n steps. At the ith step, we'll see realization of xi from the ith distribution. And I'll assume we can always rename them. So you'll first see the first distribution, the second one, the third one. The goal is to immediately accept or reject that value. You can only accept one value. So there are going to be n numbers. If you knew all of them, you want to ideally select the largest of them, the max. But notice because everything is random variable, so max is also a random variable. The question is, how large can I get a value compared to, say, the expected max of all these random variables? Okay, and let me clarify, please do ask questions if something is not clear. I want it to be interactive. So just to clarify, the goal is I want to maximize the accepted value. So I'm going to accept one value, and I want to maximize that value. And as you might see, that's why it's related to optimal stopping theory, because in some sense you want to choose the stopping time. What's the time when I select this random variable and I stop? But your benchmark is the max of all of them. So that's why it's called also the profit inequality. A profit is somebody who knows all these outcomes up a priori. Then what would they select? They'll select the max. How close can you get to that? Good, so the goal is, what can I do this? And let's say an example, say the first random variable turned out to be 4. It was uniform between 0 to 10. Remember, I know the distributions for all of them, but I don't know the exact values for all of them. I need to decide, am I taking the first box or not with value 4? Let's say I decide maybe not to take it. Okay, I go to the second one. The second one turned out to be 6. Now I need to decide whether I'm taking this or not. Remember, 4 is now gone. 6 is the option. And let's say for some reason I decide. Maybe it seems pretty good. 6 seems good. Expected values of D3 and D4 are pretty low. So I'll go for maybe value of 6. And then I continue. Now continuation is more like a hypothetical game in some sense, because you've already stopped, you've already collected the reward. So in some sense, the game has ended. But had you continued, maybe x4 turned out to be 10. Okay, so the max of these 4 random variables is 10. You got a value of 6. And I'm interested in comparing the expected value of your algorithm to the expected value of max. Good, all of these are random variables. And as you can immediately see, there's no way I can guarantee that I'll always get the max. because I don't know the future. There's always a non-zero chance. Maybe something in the future will have very high value. So the question is, what fraction can I guarantee? And this is known as the profit inequality. So the old result from the 70s, due to Krengel, Suxton, and Garling, they showed that you can always come up with an online policy, an online algorithm that in expectation gets at least half of the expected max. So expected max is what you want to get, but you can get at least half of it. So it's not terrible. It's only like a constant factor loss. And yeah. And I'll talk more about what is, and turns out to half is also the optimum, the tight constant. Okay, before I proceed, any questions? So this is the, as I'm saying, the profit inequality problem or the single item problem, because I'm just selecting a single element. And I'll use this as a motivation to come up with some techniques. And the technique we'll use is the online contention resolution scheme. This particular result, of course, has many, many proofs. As I'm saying, it's 40, 50 years old. So yeah. But yeah, so that will motivate the definitions. Good. So, and this is now become a very big area. It has many, many applications to online algorithms you can immediately see, but it has also many applications to mechanism design. For instance, you can think of these are like some kind of bidders coming one by one. You have one item to sell. Who do you sell the item to? So there are such high level, these are the high level connections, and I'll get into it more towards later part of the talk. Good. So profit inequality, as I'm saying, half is this. Let's first see why half is tight. Okay, just a simple example. So imagine you just have two random variables, and x1 takes value 1 deterministically. So x1 is always 1. x2, on the other hand, can sometimes take a very large value, and otherwise it's 0. So x1 is 1, and x2, the second distribution basically is with epsilon chance, it's going to be 1 over epsilon, and otherwise it's going to be 0. Now, in some sense, any online algorithm, either it takes x1 and gets value 1, or it goes for x2, but again, in expectation, x2 only gives a value of 1. So any online algorithm cannot get more than 1. However, the max of these random variables, these two random variables, is going to be roughly 2. Because with epsilon chance, x2 is the max, and it takes 1 over epsilon value. And with 1 minus epsilon chance, max is 1. So the expected max is roughly 2, 2 minus epsilon. Think of epsilon being very tiny. But no online algorithm can get more than 1. And that kind of shows that, okay, you cannot get max, you cannot get even factor 2. But turns out the profit inequality result is saying that this is in some sense the worst possible example. So for any distribution, not just two random variables, with even millions of random variables, I can always guarantee a policy which will get me at least half of the expected max. Let me pause for a second in case there's something clear. Okay, good. Nice. So we'll be going towards proving it. And I'll take more, you can say, CS theory kind of an approach, approximation algorithms kind of an approach, where we write some kind of an LP relaxation and so on. But before I do the LP relaxation, let me make one assumption for simplicity. Rather than working with arbitrary, non-negative random variable distributions, I'll be working with a special class of distributions. I'll call them weighted Bernoulli distributions, where xi takes value vi with some probability pi, otherwise it's 0. So this is only for simplicity. All the things that I'll talk about can be generalized to general distributions. But the heart of the problem, and especially connections to online contention resolution schemes, they are much more clear if you just talk about this subfamily of distributions. So one way of thinking about this is you have these different random variables with kind of different customers. The ith customer shows up with probability pi. If they show up, you know that they'll have a value of vi. Otherwise, they don't show up and you have a value of 0. Okay, so in some sense, this is what I'm going to call the weighted Bernoulli distributions. And for simplicity, I'll talk about this. Good, so now if I have this problem, I want to talk about the expected max. That's my benchmark. So usually what's the strategy that we take in approximation algorithms? We come up with some kind of a LP relaxation for the problem, trying to capture the optimum benchmark. That's what we'll do, and then we'll try to somehow round it. And the rounding will motivate the definition of online contention resolution. So first, let's write the LP relaxation. Here's a simple LP relaxation. So you have variables yi. Intuitively, yi represents what's the chance that ith random variable is the maximum. Okay, so that's why I have summation of yi is at most 1, because one of them is going to be max. Each yi is at most pi, because remember, if something is 0, I don't take it, because 0 is not useless. And xi takes value vi only with probability pi, otherwise it's 0. And when xi takes value like vi, it will contribute vi value. So my objective is summation over I vi, where vi represents the chance that I is the max. Summation yi is at most 1, and y is less than or equal to pi for all I. So I claim that, is this clear why this is an upper bound on the expected max? Because I can think of basically yi as the probability that I is the max. So in general, this can only be higher. Any questions? So, I mean, I'll not get into it. Turns out this, yeah, question in the back? Sorry. So the question is, why do I want to talk about LP relaxations? Why do I want to talk about approximation algorithms? This is a stochastic problem. You can define an optimal policy for this problem. It's some kind of a Markov like MDP, or turns out it has a very simple structure. So today I'm interested in the benchmark of hindsight optimum. So there are applications where you are interested in comparing yourself to the expected max. An alternate benchmark would have been whatever is the best optimal online policy, what that can achieve, can I design that in polynomial time? So there's a lot of work on that direction as well. But today there are also lots of applications where you care about comparing to the expected max. And hence I'm not talking about dynamic programming, but dynamic programming based policies can also be given. And another thing you might ask is, for this problem, the optimal policy, in some sense the optimal online algorithm can be written as a dynamic program. So you might as well say okay, I want to maybe directly argue that gives me a half approximation to the expected max. Turns out usually the optimal dynamic program it's pretty complicated to study. A more LP-based approach is easier to understand. And again, the real reason I'm talking about it right now is because I want to motivate the definition of online contention resolution. And that would make much more sense if I start this way. Okay, good. So here's the LP relaxation. And the question is, gives you a bound of on expected max. Turns out this LP relaxation has an integrality gap of some kind of roughly 1 minus 1 over e, so 0.63, which is more than half. But we don't need to understand the integrality gap right now. But the point, of course, is once I have the LP relaxation, if I can design an online algorithm that gets at least half of the LP value, so the LP value is summation over I vi, then I have a half approximation to this LP relaxation benchmark, which is only more than the expected max, so I have the half profit inequality like a result proving this. And this is what will motivate the definition of online contention resolution scheme. Okay, I want to design an online rounding algorithm which knows these yi variables. The question is, how do I go about taking them? Okay. Now let me define the OCRS problem a little bit more formally. So one more assumption is actually, this is a subtle point, maybe, yeah, if you don't get it, but so yi you can always assume to be are either 0 or pi, in the optimal solution. They will never take an intermediate value because in a worst case instance, you can always imagine that you've reduced the pi, and that will only, the LP relaxation value will not change, but your algorithm's value can only decrease because you've reduced the pi. So you can always imagine yi is either 0 or pi. Again, it's a subtle point. If you didn't get it, it doesn't matter. Okay, so now let me introduce this definition of online contention resolution. And it has an interesting history. So Saeed Ali studied something similar. He called it the magician's problem. He did not define it as online contention resolution in 2011 paper. I think it was in FOCS. But later on, we realized that maybe a better way to view this approach is something called as online contention resolution scheme, and that was formally defined by Moran Feldman, Ola Svensson, and Rico Zinklusen in a SODA 2016 paper. Okay, so that's why I'm calling it online contention resolution scheme. But in some sense, the problem was at least appeared in Saeed Ali's 2011 work, and maybe even earlier, because the approach is somewhat quite natural. So now what's the online contention resolution? So it's a rounding problem. So now you can forget about the profit inequality problem that we talked about. The precise question is the following. I give you some y1 to yn. They are between 0, 1, such that summation of over I yi is less than equal to 1. You can think of equal to 1. again, like going back to our old problem, like yi kind of represents what's the chance that the ith random variable is the max. Good. And now what's going to happen is you have again an online problem. At step I, like in the first step, second step, third step, in the ith step, the ith variable is going to be active with probability yi and inactive otherwise. Okay. So it's in some sense like in the weighted Bernoulli distribution, it's saying like somehow the ith random variable, whether it takes a value of vi or it's like kind of 0. So the crucial thing is summation yi, because of the LP relaxation, I can assume it's like at most 1. So on average, only one of them is going to be active. But because these are independent random variables, sometimes maybe 2 of them show up, sometimes 3 of them show up, and sometimes maybe none of them shows up. You want to kind of come up with an online rounding algorithm which selects always at most 1. So what's an alpha OCRS? Think of alpha as like factor half or something. So it's an online rounding algorithm that always selects at most 1. So it has to decide at this point, like whenever element I is active, is it taking it or not? If it's inactive, you'll always discard it. If the ith element is active, you have to decide immediately whether you want to take it or not. The guarantee that you want is that each element I, when it's active, you want to take it like on average, like you can say like with half a chance. When it's active, if I don't condition on it being active, like half times yi. So in some sense, remember my LP was having an objective value of summation over I, yi, vi. As long as I can get each of them, I cannot get them with exactly probability yi because this is a relaxation. It's not exactly the max, an online problem. But as long as I can get them at least half of the times, each of them individually, then I have a half guarantee. So, and by linearity of expectation, it immediately, if you can get an alpha OCRS, it will imply an alpha profit inequality or the alpha approximation to the online selection problem that we talked about in the last slide. So this is the most important slide. So let me be very slow here. And please do ask questions if something is not clear, because we'll be talking about more and more generalizations of this problem and so on. So again, let me repeat the setup. You're given fractional values yi's. They sum up to 1. So on average, only one of them will show up. But each of them independently shows up. So sometimes more might show up, sometimes less might show up. Whenever something shows up, the question is, okay, which of them do you select? If multiple of them show up, then which one do you select? So if 2 of them show up or 3 of them show up. In particular, you want to even make this decision online. So I tell you whether the first one is showing up or in some sense active, inactive. The formal terminology, it's called active. If it's active, you have to decide, are you taking it or not? If it's inactive, you always discard it. But multiple of them could be active, so you need to be careful. And you want to guarantee that each of them, you're taking them at least on average with like alpha chance if they're active. Okay, questions? Let me maybe to give more clear, let me show you why I can assume at least alpha is a quarter. So it does not show me 1/2 profit inequality. It will show me a 1/4 profit inequality. In the next slide, I'll improve this quarter to a half. But yeah, as a warm-up, let's do a quarter. And here's a very simple online algorithm. It does the following. It's looking at these random variables one by one. At the ith random variable, with half a probability, it will just discard it without even looking at whether it's active or not. With the remaining half chance, if it is active, I'll take it. So that's the algorithm. I claim that on average, it's going to take every element with at least like a quarter chance if it's active. Good, so let me clarify. The algorithm is, I'm using the word consider in the sense that you're even going to think about taking it or not with half a chance, otherwise you'll just immediately discard it. So I'm going to consider it with probability half, and then I'm going to select it as long as it's active. And I've not selected anything before. The claim is that this algorithm is always going to select each element at least with a quarter chance. Again, kind of, it makes sense. Intuition is that, okay, earlier, on average, you were selecting, if I was greedily selecting each of them whenever it's active, you can create simple examples that you could be in trouble. You could be selecting some element pretty much all the time. However, now, because in some sense, I'm ignoring each of them with probability half, intuitively, kind of, on average, I'm only selecting at most half an element. Because summation yi, in some sense, has now been reduced from 1 to a half. So on average, I'm selecting at most half an element. So at least half the times I don't select anything. But a bit more formally, so I want to argue that each element is going to be considered at least with a quarter chance. The way it's going to be considered, probability of I being considered, is first of all, you probability that you reach I, in the sense that you've not selected anything before I, and that you consider I on reaching I. Now, probability of reaching ith random variable is at least probability that you reach even the last one. And probability of considering I on reaching it is a half. And now probability of reaching n by a simple union bound, because on average, you are selecting each element at most by yi over 2. So you are, by simple union bound, you're reaching even the last element with 1 minus half probability. You are basically reaching even the last element. So this half times half gives you a quarter. Okay, so again, please ask questions yeah. So this slide is somewhat very important because it will, gives the intuition. So again, here's a simple online rounding algorithm. It basically says okay, with half a chance, I'm just going to ignore the next one. With the remaining half, I'm going to take it as long as it's active. It's active with probability y. Good, and the reason roughly you're getting a quarter is because first of all, with half a chance only, I'm going to consider if I reach it. And also I'm going to reach everything with probability at least a half, because on average, I'm only taking half an element. So with the remaining half a chance, I'm definitely, because I've scaled down everything by factor 2, so on average, I'm not taking something with at least a half a chance. So I'll reach everything with at least a half chance. Good. And let me also compare it to talks that you've seen, for instance, yesterday, online correlated selection. The setup is somewhat different. Here, kind of, the Ys are known to you a priori. There's nothing it's not that the Ys are being revealed to you online. The Ys are known to you upfront, all the y1, y2, y3. But whether the ith element is active, that realization is only being revealed to you at the ith step. So in that sense, it's again an online rounding, but because of different reasons. It's not because y is being revealed to you gradually, one by one. It's more about the realization is being revealed to you. So that's why it definitely has lots of applications, especially in stochastic problems. Okay, questions? Okay, so if not, then let me quickly also give you how to improve this quarter to a half. So there's a half OCRS. The algorithm is as follows. It's kind of reverse engineered in the sense that I want to get each element with half a chance on average. So I'm going to do calculate whatever is the probability of reaching the ith element. And then I'm going to consider it with probability 1 over 2 times probability of reaching it. So that on average, if I take the product, I'll get basically the half. So I'm going to take it with probability half. And the proof is somewhat, okay, so all you need to kind of argue is that this is a valid distribution. It gives you a valid distribution, and turns out this is not difficult to show. You need to show just that probability of reaching each ith element is at least a half. You can prove by a simple induction that there's a closed form expression for probability of reaching I. It's given by this 2 minus summation of yj's for j less than I over 2. And the proof is a simple two-liner. The chance of reaching, basically I want to prove this expression. Probability of reaching I plus 1 is the probability that you reach I times you don't select the ith one. So that's the chance of reaching I plus 1. And what's the chance of not selecting the ith one? It's basically the chance that you select basically ith one is basically yi if it's active times the probability that it's considered on reaching this. If you just substitute them, it will easily work out. Again, the exact math is not super important. I just want to illustrate more the ideas to you. So the high level idea of getting, first of all, the quarter was you just do kind of a greedy thing, reduce each y by a factor of 2, and then select if it's active. The approach of getting a half OCRS, the tight half, is some kind of a reverse engineered. Okay, you shoot, okay, what's the smallest probability with which I need to consider the ith random variable so that I get a half. You can calculate this, and turns out that is a valid distribution and everything is fine. Okay, so, and again, this was already in the 2011 paper of Saeed Ali, the half OCRS. So this again, as a corollary, it gives you a half profit inequality, a result from the 70s. So it gives you a new proof. Again, depending on your background, you might find it more natural, less natural, that's a different question debate. But yeah, it's an LP relaxation based approach. You write an LP relaxation and perform this online rounding. Okay, questions? Yeah.
I have a question about the LP that you use here. So it seems to me that there's this possibility of writing pattern constraint, for example, the sum of yi is at most the probability that at least one of these elements is
Yeah, so the question is, why did I write this LP? Can I write a stronger LP for this problem, for the online problem? Turns out here, okay, it doesn't matter for this particular single item selection. It's already giving you the half. But as I was telling you, this LP has an integrality gap of something like 1 minus 1 over E. Can you write a better LP which has a better integrality gap? And there are better LPs known. If you've heard of things like border constraints, it has in interpretation in economics. You can write some kind of subset constraints, like what's the chance for a subset of elements that the max falls in there, like or none of them is active. So there are stronger LPs known, and they do help you, especially if you go to like a larger setting such as matchings or something. So yeah, so I'll mention that pretty much like on the last slide of the talk. But yeah, I won't be getting into it. You can try to write stronger LPs, especially for these stochastic problems, and then try to again do some kind of online contention resolution or like online rounding with respect to that stronger LP. Yeah, so yeah, that's definitely a very valid approach. In some sense similar to like even in offline approximation algorithms. I mean, why do you work with the standard LP? Maybe you look some kind of a Sharale-Adams, SOS, sum of squares hierarchy, or like some other, like you can always try to make your LP stronger, and that might add power, and it does add power for some problems. Turns out for single item profit inequality, it doesn't make a difference, but it does make difference for other problems. Good question. Yeah. Okay, so again, to summarize, what we saw is basically an LP-based rounding approach for this. And this again factor is tight, factor half for online contention resolution, simply because, I mean, profit inequality half was tight. If you could do something better here, yeah, you will get. I mean, again, or more direct proof is when you have two random variables, y1 is roughly 1 minus epsilon, the y2 is roughly epsilon. If you try to take y1 with more than half a chance, you won't be able to take y2 with at least half a chance, so that's why half is tight. Okay, so here's the outline for the talk. I just described you what is the online Bayesian selection or the OCRS problem for the single item setting, where you're only selecting a single item. Then there's like lots of work in the last decade on how to select multiple items. Like what if I can select k of them? Or what if I have some kind of a matching constraint, some packing LP, some matroid constraint, matroid intersection. There's lots and lots of work. I'll be only talking about a few of them. Again, giving you some high level ideas, what kind of results are known. Yeah, I mean, I can easily, like all of them are pretty much separate papers. So yeah, there is like a lot happening. And then I'll also talk about like the third part of the talk will be about some implications to some, say, posted pricing mechanisms, which is mechanism design when you're trying to sell this item maybe to bidders arriving or something like that. There's something called stochastic probing. The problem also has, this technique also has implications beyond linear objectives. So if I can guarantee you each element, I'm getting you at least with like some half a chance as what the LP wants. Linearity of expectation helped me to deal with linear objectives, but turns out even submodular objectives, beyond linear objectives, you can actually get something out of it. Maybe you have to impose some other constraints, so there's slight modifications. And then it has also connections to things like matroid secretary. And again, like these are just a few examples. There's this technique of OCRS and broadly the area of profit inequalities and so on. It has many, many applications. Again, these are just like a few illustrative examples. Yeah, I'm happy to talk to you more about it. Good. Okay, so let's continue. So let's first talk about this multiple item setup. So the setup is now I'm giving you some kind of a downward close or a packing constraint, say like a cardinality constraint. You can now take k elements, or I'll give you a matroid or matchings or something. Again, you have the same n independent distributions. For simplicity, again, I'll focus on this weighted Bernoulli distribution where xi takes value vi with probability pi and otherwise it's 0. I'll talk towards the end about the extensions. At step I, you're going to see the realization of this ith random variable. You have to immediately select or reject. And the goal is now to maximize the sum of the accepted values. So remember earlier I was only taking one value. So I was just interested in maximizing that value. Now I'm interested in maximize the sum. Good, and of course I can only take a subset of elements as long as they are feasible. They satisfy my cardinality constraint or my matching constraint, whatever is the setting. And as before, I can write an LP relaxation for the problem. The expected max feasible set is given by a similar thing like summation over I vi vi. Vi is at most pi, and you have some kind of a feasibility constraint. Like earlier I was putting summation vi is at most 1. But if I have a cardinality constraint, like I can take k of them, then I'll put maybe summation y is less than equal to k. I can put a matroid polytope. I can put a bunch of other things. The question is, I can solve this LP relaxation. It's going to give me some valid upper bound on the expected max feasible set, the expected optimum. And then I'm interested in the online rounding part, which is also called online contention resolution. Good? And yeah, as long as I can get something which is alpha, like say half of this value, then I can have a alpha approximation for my online Bayesian selection or the profit inequality problem with multiple items. Good. And so the next few slides will be more about like different kinds of constraints and what kind of rough techniques people have been using. Okay, so first let's do the cardinality constraint where you can select k of these elements. So again, so the OCRS setup, like from the last slide, like it will effectively reduce to the following thing. You're given these fractional variables, y1 to yn. They sum up to now k instead of 1. At the ith step, you're going to see whether the ith element is active or not with probability, independently with probability yi. You need to immediately select if it's active, decide if it's active, whether you take it or not, whether you accept it or not. But you can only take k of these elements. So on average, k elements will show up, but sometimes more than k might show up, sometimes less than k might be active. The question is, how do I decide which k to select? While guaranteeing that for each element, it's getting selected if it's active, at least with like alpha chance, like say alpha is half or something. Good. And again, as I was saying, alpha OCRS will immediately imply an alpha approximation for my original problem. Good. So the claim that I'm making right now is for multiple item selection when k is large, like remember like earlier we were talking about k equals 1. When k is large, you can actually get some approximation factor or approximation ratio which is getting very close to 1. So you don't even have to lose a constant factor. The approximation ratio kind of starts approaching 1 as k increases. Intuitively, that kind of makes sense. Is like you're selecting, say, 100 items. Now I can afford to make a few errors. Like I have some room to make errors. Earlier I was only selecting one element, so if I made an error, things would be bad. But if I have 100 elements to select, if I make a few errors here and there, hopefully I can cover up. That's the intuition, and precisely that's what shows up. So one can show that you can get a 1 minus epsilon OCRS. And the point is, epsilon is roughly like 1 over square root k times some maybe log factors. Okay, so and this has a very simple proof. So I'm going to present this. Why the right answer is, say, tends to 1 as k increases. Okay, any questions? Again, please do ask questions. Okay, so if not, then, so what's the algorithm? The algorithm is just the following. You have these elements. The ith element, I'm going to, with epsilon probability, where epsilon will be chosen something like this, I'm going to just ignore it. With a small chance, I'll basically not even look at it. I'll just immediately discard it. With the remaining 1 minus epsilon chance, I'm going to greedily take it. Basically, if it's active, I'm going to take it. If it's inactive, I'm not going to take it. So this is kind of trying to generalize that 1/4 approximation that we had. Like, yeah, there epsilon was chosen to be half. Now I'm choosing epsilon to be something very small as k increases. And the point is, because of simple Chernoff bounds, you want to argue that things are good, like high probability holds. Because remember, summation y is at most k. If I multiply everything with like 1 minus epsilon, because with epsilon chance I'm ignoring, now summation in some sense, the new yi is k times 1 minus epsilon. Hence, the chance you would say like, okay, because it's k times 1 minus epsilon, the chance that you become infeasible because of Chernoff bounds is going to be extremely unlikely, as long as epsilon is chosen appropriately. And that's precisely the reason. So because of concentration bounds, and again, to say it more formally, what's the chance that the ith element is considered? It's probability that you reach I, in the sense you've not already exhausted your entire budget of k before I, and probability that you consider it on reaching. So probability of reaching I is at least the probability of reaching even the last element times probability of considering something is exactly 1 minus epsilon. I'll argue that probability of reaching n is at least like say 1 minus epsilon, so you'll get a 1 minus 2 epsilon OCRS. And why is the probability of reaching n at least like 1 minus epsilon? It's because this is basically probability that sum of n independent random variables with the sum being k times 1 minus epsilon. What's the chance that that exceeds k? So I have these n independent random variables, which is basically yi times 1 minus epsilon. What's the chance that their sum exceeds k? By a simple concentration bound like Chernoff or whatever, you can argue that as long as I choose epsilon to be like something like 1 over root k, again, the intuition is, okay, on expectation k, so standard deviation and all will say like, okay, it will be k plus minus square root k. So as long as you make the expectation to be like k minus square root k times some polylog so that you can have like with high probability, you are done. I mean, you're kind of done because you have things high, like concentration kicking in and things are good. Okay, so that's why like the proof goes through. So you can get an approximation ratio tending to 1 as k increases. Turns out you can actually even shave off the square root log. The right answer is roughly like 1 minus 1 over square root k, up to some constants here. So Saeed Ali basically, it's in some sense you can say like a fancier version of the half OCRs that we saw. You have to again some kind of cleverly reverse engineer, choose these parameters carefully, and that gives you like even like you can get rid of the logs. But yeah, I won't get into it because it's much more involved. There's a recent paper of Matt and his student who gives us relatively simpler proof of the same result, but it's still not trivial. It's not like a two-liner. Yeah. Okay, questions? That's all what I want to talk about, this cardinality constraint. Yeah, so now I'll move to some more general settings. Okay, like again, the repeated theme that's going to be is that I'm going to talk about like motivation from say the online Bayesian selection problem. But the underlying technique is this OCRS, where I give you a fractional solution in my feasibility polytope, like it's selecting at most k elements. And then I want to round it. I want to make decisions on the fly, whether I take the ith element or not. Okay, so now let me talk about something called packing LPs under some large Bethe assumption. This is in some sense a generalization of the uniform metroid that we just saw on the last slide. Okay, so what's the setup? Now you have m resources. So it's an LP with m constraints, and each resource has k copies. Okay, there are like k copies of an element if resource arrive. N requests arrive. Each request on arrival, it's going to ask for a vector of resources. So it's going to say like, give me 0.5 of resource 1, 0.7 of resource 2, some different values of different resources. Okay, you need to decide immediately whether you want to select it or not. The reward that it's going to give you, it's going to be drawn from some distribution. So you get to see the ith request, you get to see how much reward it's going to give you. You need to immediately decide, are you going to accept it or not? If you accept it, you are going to consume exactly like this vector, that much resources. Basically, the jth coordinate of this will tell me how much I have consumed the jth resource. Immediately accept, reject, and I want to maximize the sum of the values. Okay, so maybe the LP relaxation is relatively easier to think about. Again, you have summation of yi, vi objective. The constraint I have is basically a packing LP. So I've assumed for simplicity that each dimension you have like exactly k copies of a resource. So you have you have m such constraints. M is the number of resources. And the constraint basically says like if you sum up like whatever you've selected, yi is how much you've selected the ith request, that times the resource consumed, this sum up should be sum up to at most k. And again, y is at most p. Okay, is this making sense? This is in some sense a generalization of the last problem where you are selecting k elements, because if I work with one dimension, this is precisely the same thing. And you can even think of this as just like a 0-1 kind of a thing. Yeah. Good, and again, like a simple argument, like repeating what we did from the last slide, can say that as long as k is sufficiently large, like something like, as long as like you can get a 1 minus epsilon approximation as long as k is sufficiently large. And the right dependency will be again like epsilon is roughly like 1 over root k. There will be again some polylogs here. Like if I do the naive approach, there's like an extra m that will appear because I need to take a union bound over m different dimensions. So the right thing will be like epsilon will be as long as epsilon is at least like satisfies this, then you can get the right bounds. It's again, as I'm saying, the proof is the same as the cardinality constraint. Simple Chernoff bounds, because in expectation, each resource I'll be consuming k times 1 minus epsilon, because like with epsilon chance, I'm going to ignore our ith request, and hence I can take a simple union bound and try to prove this bound. There are something better known, but I won't get into it. It gets more technical, and like there are a few other things that arise. So, but yeah, again, I want to give you like a high-level idea of what kind of problems people are studying, what kind of techniques they are designing. And you can again try to improve some of these log factors. Okay, more question about this second slide? Like each slide is somewhat in some sense a different setting, like same setting, but like generalized, like different packing constraint, different polytopes. Just to give you some flavor of what's happening. Okay, so let's go to matchings. third, like another setup. There again, matching always has like a few variants, whether you have vertices arriving, edges arriving, vertices arriving one side, two side, and so on. Let's start off with, say, a single one-sided vertex arrival model. This is something that you've seen a lot in the last 2 days. You have a bunch of offline nodes and online nodes arriving one by one. On arrival, the ith node tells you that what are its edge weights to all the offline nodes. So it's a bipartite graph. You have a bunch of offline nodes and a bunch of online nodes. You need to immediately decide are you going to accept it or not. And you want to maximize the sum of the edge weights that you accept. I'll assume again like some kind of a simple distribution. Think of it like whether the ith online node shows up or not. So it shows up with probability pi. If it shows up, then it has some known values vij's. Otherwise, the ith node does not show up and the edges weights are 0. So again, simplified so that I can write a simple LP relaxation. Again, things can be generalized to beyond Bernoulli distributions. And as you might guess, like, okay, the natural LP relaxation here is the following. Summation over all ij, yij times vij. You want to argue that ith node is on average selected at most pi because only with pi chance it shows up. And you have some standard like matching constraints. Each offline node, on average, it's getting matched to at most one online node. And again, like commenting on what Zihi was earlier asking, like, okay, you can write potentially stronger LP relaxations, hoping to get better. For some problems, it does make a difference. Here, it won't make much of a difference. Okay, so now the question becomes again, if I give you some kind of a fractional solution to this LP, can I round it online, which is the OCRS problem, in this kind of a vertex arrival model? By vertex arrival, I mean like when the ith vertex shows up, it shows you all the yij's simultaneously and its realization, rather than showing you edge by edge. So again, turns out there's a simple half OCRS because this problem can pretty much be reduced to back to the single item setting. And what's the algorithm? On arrival, the ith node chooses one of the j's at random with probability proportional to, in some sense, yij. So it's saying like when the ith node shows up, it's just going to choose one of the offline nodes with probability proportional to yij's. And now that jth node is just going to decide whether it's going to accept ith node or not. The reason this problem reduces to like a single item problem is because from the perspective of the jth node, it's kind of just a single item problem. On average, this jth node is only going to receive, because of this constraint, on average, it's going to receive one request, and different i's are anyways independent. Hence, you can argue that basically the same thing as the single item thing still works, and you can get a half approximation. Again, like giving you just an idea, like it's just saying that, okay, it's pretty much the same as the single item problem. You have to do the additional step. As soon as the ith element comes, just choose one of the j's at random with probability proportional to the LP value. And that gives you, that basically reduces to the single item. Yeah. So the second constraint is using the fact that, that this is valid, choosing one of the j's at random. Questions? Good. If not, and again, half is tight because this is a generalization of the single item problem. You can also talk about general matchings, like what happens with edge arrival, for instance. At ith step, maybe some edge ij shows up, taking some value with some probability dij. You need to immediately decide are you going to take the edge or not. You want to maximize the sum of the matches in the edges. Again, you can write some kind of an LP relaxation. Let's say, again, for simplicity, it's a weighted Bernoulli distribution, some kind of a distribution, like a natural LP relaxation. The question is, how can I do the rounding? Turns out this was actually studied a lot. This is an EC paper of 2020 of Thomas Ezra, Michal Feldman, Nick Gravin, and Gavin Tang. And they showed you can get at least like a 1/3. They even showed 1/3 plus some constant, 1/3 plus something, but 1/3 is relatively clean. So I'm just quickly telling you like the 1/3 approximation. You can even do something better than 1/3. Okay, is the setup clear? So again, like the OCRS question is, if I give you a fractional solution, some y's, which are feasible in this polytope, and if now the ijth edge is active with probability yij, are you going to take it or not? You have to make this decision. And of course, the constraints that you have is no vertex should be matched more than once. It should be a valid matching. Okay. Turns out this again has like a simple algorithm. It's some kind of a general, like a variant of the half profit inequality that we saw, like where you take the ith element with kind of, again, like a reverse engineered approach. So here the probability turns out to be 1/3 times probability that you calculate like what's the chance in your algorithm that both I and j are currently unmatched. So you can show this, and I feel like the calculations are a little bit involved, and seeing them especially like in a slide. So that's why I'll maybe skip the calculation, but all I'm saying is the proof is just like, again, a 2-3 lines. You can argue that this is a valid distribution, a simple case analysis that gives you that it's a 1/3 OCRS. In this setting, 1/3 is not tight. As I'm saying, there's already 1/3 plus epsilon known for some constant epsilon, but even that's not tight. So for instance, here's an open question. For edge arrivals, we don't know the right answers. In general, for like things like matroid intersection and so on, we don't have good answers. We know constant approximations, but if you really care about the exact constants, that we don't know. Okay, so this is the matching setting, the edge arrival. Any questions? If not, then let me move to one more setting, the matroid constraints. Again, it might start getting a little bit boring. I'm talking about so many settings and so many things. I want to illustrate more the ideas. Matroids will now require a bunch of new ideas because, as you might guess, like matroids have a lot more structure to it. But let me first again briefly introduce what the problem is. You have independent distributions. At the ith step, you see the realization of the ith random variable. Immediately accept, reject inside your matroid while being independent, feasible in your matroid. Maximize the sum. OCRS is I give you a fractional solution inside your matroid polytope. So the matroid polytope is for every subset summation yi is at most the rank. Element I is active with some probability yi, whether you accept it or reject it. And an alpha OCRS is, or a half OCRS, whatever factor you're aiming for, is as long as you can guarantee that the ith element will be taken at least with alpha chance if it's active. And by linearity of expectation, it will give you like the alpha profit inequality for the corresponding setting. Good. Yeah, so this is something like that was actually the motivation behind this paper of Moran, Feldman, Ulla Svensson, and Rico's inclusion. So this is the reason they defined online contention resolution schemes. I'll later talk about something called offline contention resolution schemes. They were defined much earlier. They were defined in 2011. So the motivation of this paper was more trying to extend those techniques. So all these problems make a lot of sense even offline, in the sense that if I give you each of the elements I, whether they're independently active with probability yi, if I give you which of them are active, how do you select a feasible subset of that? So you can ask those questions. And they have many applications in submodel optimization. I'll briefly talk about it in the end. So that was their motivation. And they said, okay, like how can I define an online contention resolution, especially for a matroid constraint? And they came up with a nice idea of designing a quarter OCRS. So it's some kind of a generalization of the single item quarter OCRS. So recall what was the single item 1/4 approximation. You kind of was saying that each element I just ignore with probability half. Otherwise, I take it if it's active. In other words, it was saying like rather than working with yi's, work with yi tildes, which are yi/2. And then you are greedy. Like the ith element, it shows up with probability yi tilde. And if it's active, you just take it. So I want to somehow come up with a similar approach for a matroid constraint. And in some sense, you want to guarantee that even if your element was the last element, it has a pretty good chance it will not be spanned. It's still feasible to take it, and you can take it. Turns out, naively, this approach does not work, because you can have some weird examples, such as this hat example. So I'm working with, say, the graphic matroid, so it should not be a cycle. Here's a valid, feasible fractional solution. So the bottom edge has value 1. All the other edges have 0.5. This can be thought of as sum of two trees, like where the first tree, sum of two trees, each having weight half. Like this edge, the first tree only has like these left side edges along with the bottom edge. The second tree only has the right edges along with the bottom edge. So I'm saying it's a valid fractional solution inside your graphic matroid polytope, or basically the matroid, the acyclic graph problem. And here, like if you see, like if you try to even like round down like each of the yi's, if you reduce them to 0.25, like say half of their 0.5 values, there's a very good chance at least one of them, these hats will complete. Like both of the edges show up, and then you take them. And if now your like bottom edge is arriving in the end, most likely it's already spanned, in the sense that you cannot take this because one of these hats is complete, and then the bottom edge will form a cycle, so it will not be feasible to take this bottom edge. Okay, so you need more ideas. Like all I'm saying is a naive approach of just like scaling down your original fractional solutions with like some constant factor and then just greedily selecting if it's active does not work because of such examples. And of course, like, okay, this example, there are easier fixes, but you can come up with more complicated examples where there's no obvious fix. So the powerful result of this like Moran, Feldman, Ola, Svensson, and Rico's inclusion was that you can actually get a quarter approximation. You can still guarantee each element is going to be taken, at least with a constant chance. Okay, so what's the high-level idea? So the main result, as I'm saying, is a quarter OCRS. So you again start off with reducing each yi by like a factor 2. But somehow you have to be more careful. So you're going to somehow break your matroid into a bunch of layers and then be greedy in that sense. So let me say a little bit more. So here's like, imagine like the outermost layer represents all your n elements, so n0. So these, I'm going to kind of, in some sense, come up with layers of these elements. So n0 represents all the elements. N0 represents a subset of these elements which are in some sense have a higher priority. N2 represent even more important elements. N3 represents kind of the most important elements. So I'm defining some kind of a priority for these elements. Alternatively, you can think of these are like some kind of a layering. So each element, each of your elements, n elements in your universe, they are going to be somewhere in one of these layers. Okay, and the main challenge is, okay, how do I cleverly define these layers? But once these layers are defined, my algorithm is kind of like basically a greedy algorithm. It's just going to say, like, if your element is, say, in some ith layer, it's going to, like, suppose you're in this layer, it's going to imagine that all the elements in N1 are kind of, let's say, already taken. So because elements in N1, N2, N3, they have a higher priority. Let me a priori imagine all the elements in N1 have been already taken. In matroid notation, it basically means I've contracted in my matroid the elements of N1. So in this contracted matroid, I'm just going to be greedy. So if an element shows up here, I'm just going to take it as long as it's feasible to take it in this contracted matroid. So that's the algorithm. So the algorithm is somehow define this layering of all your elements. And then you take an element in the ith layer as long as it's feasible after you contract higher priority elements. And the claim would be that this gives you a quarter OCRS. Okay, so here's like another like nice idea technique. And like in particular, like for this layered example, like for this hat example, the layer would look like basically two layers in some sense. This element, the base element, will become like a higher priority element. So it will go to one layer higher. And then in some sense, you will never be able to complete a hat because it would say like, okay, imagine that the base element has already been taken. So you're never allowed to take both of them simultaneously. So that's how it's kind of addressing this hat example, but generally it applies to even more matroids. Any questions about the strategy? Like it's a nice technique. And yeah, so, and the way you construct the layers is also a very greedy based approach. Start off with just the base layer. There's nothing in the higher layer. There's just the base layer. So there are two cases. Either every element already has a good chance of not being spanned. So you kind of don't even have to worry about anything. Every element somehow, even if there's no in some sense hat hidden, that will like put any element in constraint. Like every element has at least a constant chance of being taken. Like more fancily written, like the chance that you draw a random set with these marginals y's, the chance that this is going to span your element for every element is at most a half, then you're already done. Otherwise, there's at least some element which needs care. So I'm going to upgrade this element I to the next layer. So that's the approach. So you start off with just the bottom layer. There's nothing higher layer. If everything is good, just don't create any more layer. But if some element is getting into trouble, just upgrade that element into the higher layer. And then repeat. So that's just the construction. So the algorithm is just this. Construct this layering in a greedy way, and then basically run the greedy algorithm in different layers. Of course, the main argue is why does this process halt? In the sense, like the worst case would be like you start off with the N0, and now you kind of upgraded all the elements. So now all elements from N0 have now moved to N1, so nothing has happened. Everything has been moved up. But this is where you argue that, okay, matroid constraints actually imply that at least one of the elements will remain in the base element. So you are making progress. So I won't give this proof. I mean, again, it's not very complicated, but yeah, it's a little involved. Like, yeah. Okay, so the approach is just greedy construction of these layers, and in each layer, I'm just going to take the element. Okay, questions? I feel like I'm saying too much. Yeah, so good. So the question is, when I'm constructing this layers, am I concerned about the order in which they are defining? So the way their algorithm, the work of like Feldman and all, they ignore the order. They imagine as if your element is the last one. Still, what's the chance? So that's why like this is defined as if probability. You're looking at all the elements, then the independent set. Even if your element is the last one, then what's the chance that it's spanned or not? So it's indifferent to the order, but you're correct in some sense. To get better than a quarter, those are the things we want to exploit. Because you remember even for single item, getting a quarter was easy because I was saying like with half a chance I'm not selecting anything till the end. So your element always has a chance of being selected even if it's the last one. But to improve the quarter to a half, I had to come up with this fancier approach where I was exploiting this sequence in which they arise. Okay, yeah. Okay, so that's all about, I wanted to talk about the first approach. And now I'm quickly going to talk about like the second approach using duality, which gets you even a half OCRS for the matroids. Okay, more questions? Yeah. Interesting. So the question is the resulting hierarchy unique? I don't think it's obvious. It might be actually unique. So, okay, I guess the question is, when I'm upgrading these elements, suppose two elements are simultaneously in danger, then which of them do I upgrade earlier? But I'm saying it doesn't matter, because if you upgrade any of them, the other one is still going to be in danger. It's going to be even in more danger. So eventually both of them are going to be upgraded. So in some sense, it won't matter. Good. Yeah. Good. So yeah, so the question is the quarter tight in the almighty adversary? So there are like a few other subtleties which I did not talk about too much. Is how much power does the adversary have? Is the order fixed up front? Is the order known to you, or is it being chosen on the fly? The realizations, are they known? So a quarter is tight, is not tight, is the best that we know in some settings. But yeah. So what I'm going to show you the next half for matroids, it is a half, but it does not apply to all the settings. So there are like a few things. There are still applications for which the best we know is only a quarter applies, because those applications require some additional properties, for which the half proof does not go through. Good question. Okay. So briefly, what's this duality-based approach? So the duality-based approach is, in some sense, reducing the problem into a different problem. So it says the following. Let's go back to our original online Bayesian selection problem, where we were writing this LP relaxation. So we were always using the OCRS, or an alpha OCRS, to design an alpha approximation for that problem. This duality-based approach kind of says the opposite. Suppose somebody gives me a magical algorithm who can do the profit inequality. If I can get a profit inequality half approximation, can I get a half OCRS? It's asking like the totally opposite direction, and a priori you might think like, okay, that sounds crazy. But yeah, so it's in some sense showing the opposite implication, that if I can have a good profit inequality, then I can get a good OCRS as well. I'm cheating a little bit, so it says a little bit differently. It says, as long as you have an alpha approximation for the profit inequality problem, for the online Bayesian selection, with respect to the LP relaxation benchmark. So not with the expected max, but the LP relaxation value. As long as you have an alpha approximation for that, you can get an alpha OCRS as well. So it says, in some sense, So the reason it's interesting is because it's giving the opposite implication. And the reason why it's useful for matroids is because for matroids, the online Bayesian selection problem was solved before the half OCRS problem. So this result basically says that you can, so what I'm saying is, so for this first part, the online Bayesian selection problem, there are half approximations one can design using existing approaches. In particular, there's a work of Bobby Kleinberg and Matt Weinberg, which can be extended to show that it gives you a half approximation for the profit inequality problem with respect to the LP relaxation benchmark, and that implies a half OCRS. So here, in some sense, it's a reverse thing, because I'm not using OCRS to solve my profit inequality problem, but the other way around. And yeah, because it's I want to get the right factor half. And as I'm saying, it implies as a corollary a half OCRS for matroids. You can even get similar results for other settings, such as random order and a bunch of other things. But yeah, I won't go into that. Okay, so is the result here? Okay, so what's the high-level idea of the proof? It's an LP relaxation-based approach. So think of writing an LP relaxation, a very different kind of LP relaxation, which is trying to find the best online algorithm. Okay, and it's inspired by some work on offline contention resolution schemes of Chandra Chakuri, Jan Mondrak, and Rico Zinklusen from 2011. So the idea is as follows. Think of the class of all possible online algorithms, online rounding algorithms. I'm going to define a variable lambda phi, which is basically what's the chance I'm running the algorithm phi. So you have a class of online algorithms. I'm going to choose one of these algorithms at random with probability proportional to lambda phi. So lambda phi is going to be the chance that I run the phi-th algorithm. And qi phi is what's the chance that this particular algorithm selects this element. So it might sound like a crazy LP because it has exponential number of variables and so on, but that's not the point. We just want to say, for instance, first of all, characterize it and study its properties. So the LP you can write is the following. You want to maximize some factor C. Think of this as the alpha that you're trying to maximize. What's the largest C or the largest alpha I can get, such that for each element, in expectation, you are selecting it at least with, this is the OCRS constraint, you're selecting it with at least C times yi value. The distribution over lambda phis is a valid distribution. So summation over phi lambda phi is at most 1, and lambda phis are non-negative. So I'm trying to find a distribution over all possible rounding algorithms such that that distribution guarantees that each element is getting selected at least C fraction of the time when it's active. Okay, so you might wonder, okay, why do I care about this? That sounds like a too complicated object, and why would I ever wonder? But notice, what does suffice is if I can show you that this LP has a value of, say, 0.5, then it will give me a 0.5 OCRS. It implies there exists a 0.5 OCRS, and that's what we are trying to show. Alternatively, because of LP duality, if I can show that the dual LP has at least a value of 0.5, I have a 0.5 OCRS. And this is the reason I'm saying this is the dual view. So if you have this LP, you take its dual, the dual will turn out to be nothing but this profit inequality problem with respect to the LP relaxation benchmark. And that's how you reduce it. So to design an OCRS, it suffices to solve the profit inequality problem with respect to the LP relaxation benchmark. So there's an intimate connection between the two. In some sense, you can go in both directions. So okay, I can quickly flash this. Basically, you have the original LP. You can take its dual. Again, I'm not going to maybe go over it carefully. And then you do a simple two-liner. Argue that the dual of this LP relaxation is nothing but the dual. You want to argue that the dual has value at least alpha. That turns out to be the same as whatever is the best possible online profit inequality algorithm that you can come up with. Whatever is the approximation ratio for that is the same as the value of the dual LP, and hence you get the 0.5 OCRS. Okay, so again, the proof is short, but because of lack of time, I'll skip it. Okay, so again, the main key takeaways of this part of the talk, which was the main heart of the entire thing, was that for lots of these online Bayesian selection problems, there are good online rounding algorithms that exist, which get you constant approximation for matroids, matchings, packing LPs, matroid intersection, and all of them. And for many of them, we have pretty good understanding of even the right constants. Okay, so if you have like any of your online problems, especially in a stochastic setting, a natural approach would be like, okay, so the problem with dynamic programming, with any stochastic problem, is that, okay, you can define a dynamic programming optimum, but that DP is usually cannot be solved in polynomial time. It has exponential size. However, if you write like say an LP relaxation for this, you can hope to design a constant approximation algorithm for that problem. So that's, and turns out like, yeah, that approach does work for many of these online problems even. Okay, so quickly some implications in the last 5-10 minutes. I'll talk about the implications. I did not want to spend too much time on the implications, but again, like I again want to introduce a bunch of different areas in which these things appear. So, so first, as I was saying, this has connections to posted pricing mechanisms or mechanism design. Like the classical example is the following: you have one item and you have n bidders. You want to sell this item to one of these bidders. Ideally, you want to sell it to the bidder which has the highest value for this item. So it has implications in, say, some government settings, like the government has a spectrum. Different companies can potentially use that spectrum for different purposes. The government wants to give the spectrum to the company who will actually maximize the welfare for the society, like which will be able to put it to the best use. Maybe should I use it for radio? Shall I use it for internet? Shall I use it for something else? So that's the high-level motivation. And the challenge becomes like these bidders have some private values. You don't know their values, so you need to be a little careful. But they have like some distributional knowledge. You want to select the highest. So I'll skip the formal definition of what's a mechanism and so on. But the real thing is, turns out it's again some kind of an online problem. I mean, you can think of the online problem as well, where these bidders come one by one, and you want to immediately select who do you give the item to. And that's pretty much the problem that we talked about in the beginning. So these OCRS-based approaches, they give you such an thing. One thing you might be wondering is, okay, we were always working with weighted Bernoulli distributions, like how do I extend things to beyond Bernoulli distributions? So here's the standard trick. Rather than getting an LP relaxation, you get some kind of a concave relaxation. So the LP becomes the following: if it's not a Bernoulli distribution, think of some distribution. So it's yi, which is the chance that the ith random variable takes the max. And then here you put, rather than vi, you put what's the expected value of your random variable, given that it's in the top yi quantile. So if I tell you like the first random variable is the maximum, say 10% of the time, what's the maximum it can contribute? The maximum it can contribute is, if I tell you that this random variable is in its top 10%, what's its expected value? So the best it can contribute is given by this, and you can write this as your value. I mean, it might sound complicated. Turns out it's a concave function, so you can still solve it in polytime and all those things, and the tricks work. And this is the reason you can even design everything pretty much extends beyond Bernoulli distributions. So I'll skip this part. So this was the connection to posted pricing mechanism. Again, I'm just getting started in some sense. There are like lots and lots of works, matroids, all of these settings. They have implications here. Yeah, it's a big area, so I'm not getting in there. Another field is the so-called stochastic probing problems with commitment in particular. Like here, the problem is, again, you have a bunch of independent random variables. You want to select a subset of them to maximize the value. But the change is there's no order in the sense a priori. You choose in which sequence you are going to see the random variable realizations. So you can say, okay, first show me the value of the fifth random variable. Then, depending on its realization, I might choose, okay, I want to see the 10th random variable, or maybe I want to choose see the second random variable. So you can be adaptive in choosing the order. But you have a commitment constraint, which basically says, as soon as you see the realization of a random variable, you have to immediately decide, are you taking it or not? Okay, so this is the setting. So this is known as stochastic probing. Again, it has like long history. Like one of the papers that said it in a more general setting was this work of Anupam Gupta and Vishwanath Nagarajan, where they talk about like you have a bunch of constraints. One is some kind of a constraint on what you can probe. Like say you can probe, I give you a graph, you can probe at least k such elements, k of these edges. The other is what you can select. Like maybe you can, after probing, you can only select a valid matching amongst them. And the question is, how can I maximize the value? So the point is, this OCRS-based approaches, you can again like write an LP relaxation for this problem and try to round it. This OCRS-based approaches allow you to handle commitments because it tells you precisely if I probe an element, how do I make the decision whether I immediately select it or not. And if you have a good OCRS, it shows you that basically imposing commitment only loses like a constant factor. It doesn't hurt you more. So that's again like a high-level connection. As I was briefly telling, like All these things also have lots of connections to submodular optimization. The reason naively you may wonder why it doesn't work is because your objective is no longer linear. So if I can guarantee that each element I'm getting with at least half a chance, it may not necessarily work. So let me skip this part, the offline part. But you can still argue, turns out there's something called as a greedy OCRS. As long as your OCRS has additionally some extra property, like except besides having some marginal properties, each element being chosen at least half the times, you also need some kind of a greedy property. Like remember the OCRS of this algorithm of like this layering based algorithm was very greedy within the layer. So it turns out those algorithms work even for submodular objectives. I mean, you can relax this constraint, but yeah, so all I'm saying is like many of the techniques do extend even to submodular objectives, not all of them. The duality based, for instance, does not extend. There also works beyond independence and connections to matroid secretary problem. Like what if your distribution has some correlations, it's not a product distribution. The high level, you can define like a distribution to be alpha uncontentious as long as there is an alpha OCRS that exists, alpha offline contention resolution scheme that exists. So, I mean, you can study these things for correlated distributions. At a high level, the main thing to remember here is negative correlations are often easy to handle. You can still do something pretty much the same as product distributions. But if you have positive correlations, things become tricky. And we don't have a good understanding. For arbitrary positive correlations, you cannot get a constant alpha, but for some mildly correlated distributions, you can hope to get good constants. And that has close connections to the matroid secretary problem. So if you've heard the matroid secretary problem, let me not even define it. So there's a conjecture that's been open for more than 15 years. And it's known that you can restate the matroid secretary conjecture as equivalent to designing online contention resolution schemes for some particular kinds of positively correlated distribution. So as long as you can do that, you can solve the matroid contention secretary problem. And yeah, so I'll skip over the exact precise connection. But yeah, there are these connections again to the matroid secretary conjecture. So again, let me just now conclude. So what we saw is, first of all, the definition of online contention resolution, how it applies to many, many settings like cardinality, packing LPs, matchings, matroids, and so on. It has lots of connections to implications to online Bayesian selection, posted pricing, stochastic probing, submodular objectives, matroid secretary. There are other bunch of connections which I did not get to talk about. For instance, what happened if, rather than adversarial order, what if things were happening in a random order? There's again, like lots of work on random order OCRS or something called as the profit secretary problem. There are connections to two-sided markets rather than just having like one-sided arrivals. You have two-sided arrivals. There are lots of connections to some delegation problems. Again, I mean, yeah, I can point you to relevant literature if you're interested. There are many, many open directions. For instance, as I mentioned, there are open questions on positive correlations. For general positive correlations, you cannot do much. But for mild positive correlations, again, I'm not formally defining what mild means. These things are not well understood. And they have implications such as the matroid secretary conjecture. We can potentially resolve using this. This is the question. The second point is more about what Zi Huang was asking, that, okay, what if I put more constraints into my packing polytope, like for the matching problem, rather than just having some marginal constraints? What if I put constraints on subsets? Those things do help for some problems. In particular, I think David Wikes, for instance, has some papers on how he can use this to design some online better policies for matchings. Even for comparing to the hindsight optimum in the matching setting, there are such results known. So that's again, but we don't know the right answers. So it's still like a lot to be done. And as I was saying, like there are also like many exact precise constants. I mean, we saw a bunch of constants, like for matchings in edge arrival, we saw a 1/3 and so on, but they are not tight. Even for matroids with submodular objectives or with greedy properties or with almighty adversary, we don't have the right answers known. We know constants, but not the exact constants. So there are like many, many open questions, and it has implications, as I'm saying, to many, many fields. So I hope it gives you some idea, and maybe you'll be able to find some applications for your field as well. Thank you. Yeah, any further questions?
I think we have time for 1 or 2 brief questions. Divya?
Just a quick question about so can OCRS be easily combined for 2 different constraints and stuff? So if I have a matroid constraint and a packing constraint or something?
So
Does
if I understand you correctly, your question is if I give you two sets of packing constraints, if I take their intersection for each of them individually, I know OCR is? Yes. So there are results known. For instance, in particular, the original work of Feldman, Swenson, and Zinklusen, they already showed how, for instance, you can now get constant approximations for intersection of matroids. Rather than doing it from scratch, you can actually combine them. You can get, so if you care about constants, this works. If you care about, say, the optimal constants, this may not be the right way. But yeah, you can apply such techniques to take intersections of packing constraints.
Okay, thank you.
So in the single item setting, what can you do if you can select your own order of the items? So if you are allowed to select the best order of the items to prop, can you do better than half?
Oh, good. Yeah, so the question is, say I give you a fractional wise, they sum up to at most 1. But rather than adversarial order, what if you can choose the order? Turns out you can actually improve. You can get a 1 minus 1 over E. Not only for free order, even for random order, you can already get 1 minus 1 over E. And that 1 minus 1 over E is tight because integrality gap. Like you can consider the simple case where all the yi is equal to 1 over n. You can show in expectation, basically, yeah, the best you can hope to get is like 1 minus 1 over E. So that's tight, and that already works for random order, you can already get. Yeah, so you can do better than half if it's not adversarial order. Yeah, again, like I did not mention, like for instance, Wilma has worked a lot on these things like random order and so on for general matroids. As I'm saying, there's lots of work in the area. I only mentioned some works just to give you some high-level idea, and even people in the audience have worked a lot on these problems. So.
All right, any more questions? Going once, going twice, going thrice. Let's thank the speaker again.
Thanks.